Swayam Prabha. Digital India. Educated India.
So good morning to all of you. So in the last class what we were doing, we had come almost to the end of the separated flow model. The only thing which was remaining was the estimation of the frictional pressure gradient. As I have written it down, the only thing which is remaining, it is the estimation of the frictional pressure gradient and as well as the void fraction from the separated flow model. Okay. So, we were discussing it, we found out, rather we were discussing that mostly large number of empirical correlations have been proposed for this particular purpose, and the basic thing of this empirical correlation is that first we assume that we have just relaxed one particular assumption of the homogeneous flow model, and we assume that the two phases are flowing at different velocities. Okay. So, we have in order to develop the empirical approach, the first thing which we do is we assume that the effective frictional pressure gradient can be expressed in terms of something like the two phase wall shear stress into the two phase wall shear stress into S by A in this particular form, and we would like to find out either tau W Tp S by A, or in other words F W. So, if you observe this particular form of the equation and the homogeneous flow model we had developed, we find that the only assumption which we had relaxed in this particular case was that the two phases were allowed to have different velocities. Other than that, this expression is identical to the expression that we had derived for the homogeneous flow model. So, naturally accordingly we had laid down the basic assumptions of the simplified one dimensional approach, and then in order to develop certain correlations for finding out the frictional pressure gradient as well as the void fraction, they were developed on the basis of no phase change, no acceleration, pressure drop, negligible body force, such that the total pressure gradient can be made equal to the frictional pressure gradient. Okay. And after that what we did, we found out, or rather we had discussed why we have tried to develop a correlation between phi L square, phi G square, and not phi L O square and phi G O square. Okay, that means we had tried to develop a correlation between two phase multipliers which were based on the liquid portion flowing alone in the pipe and the gas portion flowing alone in the pipe, instead of the entire mixture flowing as liquid or the entire mixture flowing as vapor. The reason we had discussed in the last class, it was just because this conforms to certain limiting conditions that we had already done. So, after that we had discussed that the oldest correlation, which is also the most widely used correlation, that is due to Lockhart and Martinelli, and they had developed their correlations on the basis of certain assumptions. We had already discussed the assumptions in the last class. The assumptions I will just tell you very briefly. The first one was the two liquids, they are assumed to flow in two separate cylinders, such that the cross sectional area of the two cylinders add up to form the cross sectional area of the pipe. This was number one. The other thing is the two phases do not interact with each other. This was the most severe assumption, and I will just show you the anomaly in the results which we get just because of this particular assumption. Before we go into deriving the analytical expression and discussing the graphical correlation between phi L square and phi G square, I would just like to show you that, so that you can understand exactly this assumption is severe. Nevertheless, we take it just because it guarantees simplicity, and within practical limits, this gives us a more or less accurate estimation of the frictional pressure gradient, particularly when the frictional pressure gradient is more important than the gravitational or the acceleration component. Okay. So, this was the second assumption, and as a result, that since the two phases do not interact with one another, we can always say that the pressure drop in each of the imagined cylinder is same as the pressure drop in actual flow. Or in other words, as I have written down the two phase pressure drop is equal to the pressure drop in phase 1, and it is equal to the pressure drop in the liquid cylinder, it is equal to the pressure drop in the gas cylinder. And the other thing is the pressure drop mainly arises due to the frictional component. Okay. So, due to which we can write that the two phase pressure gradient is primarily the frictional pressure gradient, and the two phase pressure gradient is equal to the pressure gradient in the liquid cylinder is equal to the pressure gradient in the gas cylinder, and combining everything we can write that the two phase pressure gradient is the frictional pressure gradient, and this is equal to the frictional pressure drop in the liquid cylinder, which is equal to the frictional pressure gradient in the gas cylinder. So, this is finally what we come. Now, so we find out that based on these assumptions, if we can find out phi L square and phi G square, then we will be in a position to find out the two phase pressure gradient. For that, what we have to know? We have to know, or we have to have methods in order to find out the single phase pressure gradients for liquid flowing alone in the pipe, for gas flowing alone in the pipe. Now, they can be obtained when a liquid or a gas is flowing alone in a pipe, then naturally it is just single phase flow, and therefore, these pressure gradients can be obtained simply from single phase fluid dynamics. The only thing we need to know is whether when the single phase flow is occurring within the pipe, whether that is occurring under laminar flow conditions or under turbulent flow conditions. If we know that, we can find out the pressure gradient when either liquid or gas is flowing. Once we can find that out, we can find out phi L square, phi G square. Once we have found out phi L square and phi G square, then we can find out the two phase frictional pressure gradient. Right. So, therefore, the fifth assumption is that 4 flow patterns have been defined, as I have written down in my transparency, that 4 flow patterns have been defined on the basis of flow behavior when the phases are flowing alone in the pipe. That means, it can be gas laminar, liquid laminar, gas turbulent, liquid turbulent, gas laminar, liquid turbulent, and gas turbulent, liquid laminar. Last one of course, is something very rare, and so therefore, it is not widely used. Okay. So, therefore, what we do? We first find out the frictional pressure gradient in the liquid portion or in the gas portion, that gives us the two phase pressure gradient, frictional pressure gradient. Then what we do? We find out the pressure gradient when this liquid or this gas flows alone in the pipe, from an idea of whether the liquid or gas is flowing in laminar flow or turbulent flow. Okay. So, accordingly, we know the pressure gradient in the liquid portion or the gas portion when both are flowing together in a pipe. We know the pressure gradient when either of them are flowing alone in the pipe. If we divide one by the other, we can find out phi L square or phi G square, as the case may be. Okay. So, accordingly, phi L square and phi G square has been evaluated, and Lockhart and Martinelli had basically given a graphical correlation between the two. Okay. So, 1 by phi G square and 1 by phi L square, they have been plotted, and we obtain a graph something of this sort, where we find that more or less it gives you for different values of n, where n is the Blochius, or rather the coefficient of the equation f equals to k r e to the power minus n. Okay. So, n equals to 1 means it is naturally the laminar flow, n for other values of n naturally it refers to the turbulent flow, and we find that we have obtained a family of curves in this particular situation. Okay. So, this equation, this is for n equals to 1, this is for laminar flow, and accordingly we have for turbulent flow. Now, this graphical correlation can be expressed by an analytical expression. Simply if we start from the basic derivation of phi L square and phi G square from the basic single phase hydrodynamics, and we try to correlate them, then we can find out an analytical expression between the two. So, we will be basically doing two things in the class. First, we will try to find out the analytical expression, and secondly, we will take up the annular flow pattern. We will find out phi L square from the separated flow model. We will find out the actual phi L square for annular flow model, and we will find how well they two agree. From that we can have an idea regarding how accurate this model is. Correct. So, these are the basic two things which we are planning to do in this class. Once we finish off these things, we obtain an analytical expression. After that, we will be discussing about further refinements of this particular model and what are the other correlations that follow and so on and so forth. Okay, so, this is the next thing that we will be doing. Now, let us start from the basic definitions of phi L square and phi g square before, and then let us see what is the analytical expression for the two. Now, in the last class, if you see in the last slide, I had already written down phi L square, it is minus dp dz frictional for two phase, which is nothing but minus dp dz frictional liquid portion divided by minus dp dz frictional when liquid flows alone in the pipe. Similarly, phi g square was defined. Now, if we start from the basic definition, what do we get? What is this minus dp dz f liquid portion? Let us do the derivation and let us see what we arrive at. This is f liquid portion. Okay. So, therefore, this is nothing but 2f liquid portion, okay, rho L u L square, this is again liquid portion. Liquid portion means the in situ velocity of the liquid phase when it is flowing under separated flow in the conduit. Okay. Remember one thing, we are deriving everything for circular pipes of diameter d. Okay. And this divided by dl. What is dl? It is the hydraulic diameter of the liquid occupied portion. Of the liquid occupied portion. So, therefore, this is the exact definition. Now, what is this F liquid portion? This is nothing but K RE liquid portion, if I write it down, whole to the power minus n. Yes or no? And what is this RE liquid portion? This will be dl, hydraulic diameter of the liquid occupied portion, u liquid portion, this writing is a very big botheration, rho L by mu L, yes or no? So, therefore, if we substitute this here, then we get what? K rho L by mu L whole to the power minus n. Just see whether I am writing it correctly or not. Okay. And instead of this u liquid portion, we can write it down as W L by rho L A L. We can write it down. What is this A L? This is nothing but gamma pi by 4 d L square, where gamma is the shape factor. That cylinder might not be completely circular, isn't it? So, this just accounts for the shape factor, which at the end we may take it as 1. Okay. So, for the time being we would like to keep it. So, this is what is the final expression of the frictional factor of the liquid in the liquid occupied portion during two phase flow. Clear to all of you? Okay. So, therefore, or in other words, this can be written down as, it is just some simplifications that I am doing for W L by rho L gamma pi by 4 whole to the power minus n d L to the power minus plus 2 n minus n. So, it becomes d L to the power n, correct. So, this is for the friction factor. So, therefore, if we substitute F here, we get the minus dP dz for the minus frictional dP dz for the liquid portion. Just do it and see what you are going to get. At the same way, we can write down minus dp dz frictional for the gas portion also. Okay, that we will do later. So, minus dp dz frictional two phase equals to minus dp dz frictional liquid portion. What we will do? We will just substitute this f portion here, and instead of ul square we are going to substitute the expression of ul. So, that we have obtained everything in terms of known input parameters. Okay. DL is of course not known, but that can be correlated with alpha. Fine. So, if we substitute that, then what do we get? This is nothing but equal to, you just substitute and then you make all the necessary simplifications. The final thing which you are going to arrive at is something of this sort. Please do these derivations in your hostels, and in case you have any problems you can come back to me and you can ask me whether you have any doubts or something. This is equal to 2n, okay, because we will be having one is for this and other is for the liquid portion part. Okay. It's sorry, it's 2 minus n probably, sorry, 2 minus n, this is dl to the power n rho l dl to the power minus 5, correct. So, this was for frictional pressure gradient expression in the liquid portion, which is nothing but the frictional pressure gradient in the two phase system. Fine. Now, suppose this liquid flows alone in the pipe. Once we can find out these two expressions, F liquid portion we have found out. Now, when this liquid flows alone in the pipe, if we can find out and if we can divide the two, we can get phi L square. So, now let us find out minus dp dz frictional liquid flowing alone in the pipe. What will we get? If we compare with this particular equation, it will be 2 FL, yes or no, rho L, correct, UL square. The liquid is occupying the entire cross section and flowing, and this DL is going to be D. Now, the liquid has occupied the entire pipe, is not it? So, therefore, this is going to be 2 FL rho L UL square divided by D. Fine. Achha. Here what was UL, U liquid portion, it was WL by rho L gamma pi by 4 DL square, agreed. Now, it is going to be WL by rho L pi by 4 D square. When the liquid occupies the entire cross section, the liquid flows alone in the pipe. Clear to all of you? Anybody who wants me to repeat this? Initially, we had derived the frictional pressure gradient when liquid was occupying a portion of the pipe. So, for that we had derived this expression. Fine. Now, the same liquid has occupied the entire pipe cross section. Agreed? So, for that case what you are going to get instead, so for that case this F will be FL, liquid flowing alone in the pipe, rho L by D, fine, it is occupying the entire pipe, and this UL square, this UL square will be equal to WL by rho L into A, because now it has occupied the entire pipe cross section. So, therefore, this is going to be in this particular case. So, where UL equals to WL by rho L A, which is nothing but WL by rho L pi by 4 D square. Okay. Or since we are taking out D separately here, so in the same way we will be taking this D out, this will be WL by rho L pi by 4 into D to the power minus 2. We can write it down in this particular way. Okay. And similarly, what is FL equals to? This will be K R E L whole to the power minus n, right. What is this REL? In this particular case, REL was DL U liquid portion rho L by mu L. In for our case, it is going to be D UL rho L by mu L, correct. So, K, this is going to be rho L by mu L whole to the power minus n d to the power minus n u L to the power minus n. I have just broken it down so that I can substitute, I can make the necessary substitutions, fine. Or this can be written down as F L equals to k, just thing which I had written down, rho L by mu L whole to the power minus n. Instead of u L I write W L by rho L pi by 4 whole to the power minus n, then d to the power d squared to the power minus n, and there was a d to the power minus n. So, finally, it lands up to d to the power n. So, now if I substitute this F L in the expression for the frictional pressure gradient, then what do I get? I get minus dP dz frictional liquid, this will be equal to 2 k, just I will write down the expressions one by one, rho L by mu L whole to the power minus n, W L by rho L pi by 4 minus n d to the power n, or in other words, if we can substitute it a little, this is going to be 2 k, this u L square also we can substitute, rho L u L square divided by, why? This rho L u L square is coming from here, rho L u L square by d, and instead of this F L we have written it in this particular form. Okay. This form, then this mu L has come here from that Reynolds number. Okay. These derivations, they need a lot of practice, please do this, because either your thoroughness or your funda, something will be tested in the mid sem. So, that is your option, which one you want to be tested, you are going to tell that to me, and accordingly either your thoroughness or your concept, something will be tested. So, this is the final form of the frictional pressure gradient. Okay. So, this is the final form for the frictional pressure gradient, and this was the final form for the two phase frictional pressure gradient or the frictional pressure gradient in the liquid portion. So, if we divide one by the other, this by this, we are going to get phi L square. So, just divide it and see what you get. When you are dividing it, if you compare the two, you find your 2 k from here cancels out, 2 k from here cancels out, rho L by mu L, rho L by mu L, they cancel out. Just because of that, I have written it in this form. Your this part cancels out, this part, only the gamma part remains, and then this rho L cancels out with this rho L, fine. Only d L parts remain, d parts remain, and one gamma part remains, nothing else. Okay. So, if you make all the cancellations, finally probably you land up into something like by d to the power n minus 5. So, from this what do we come to know? We find out that the phi L square, the two phase multiplier, it is the the ratio of the two phase frictional pressure gradient, okay, which exists if liquid flows alone in the pipe and which exists for the two phase case. They depend on just two things, they do not depend on flow rate, they do not depend on anything, they just depend on two things. What are the two things? It is the fraction of the flow area occupied by the liquid phase and the geometry of the flow area occupied by the liquid phase. It just depends upon the two things, and this is the final phi L square which I have obtained. Similarly, we can proceed and we can come or we can arrive at a phi g square as well. Yes or no? Fine. This will again be dg to the power n minus 5, where dg is the hydraulic diameter of the gas occupied portion. Any doubts? Any doubts? You can raise your hand. We can put a delta or something sort of a thing which is the shape factor for the gas occupied portion. Okay. This can be n minus 2 by d to the power n minus 5. Okay. Delta and gamma, they can be the same thing. I can put it something else, maybe beta I will put it. Okay. This is the shape factor for gas occupied tube, gas occupied portion of tube, and dg is the hydraulic diameter of gas occupied cross section or gas occupied portion. Fine. So, in the same way we can get a phi L square and we can get a phi g square. Okay. Now, usually we can take these two as equal, or else we can assume that more or less, since from the separated cylinder model, what was the first assumption that I made, first assumption that was written down in my transparency slide, they flow in two separate cylinders such that the cross sectional area of the two cylinder is equal to the pipe cross section. So, therefore, in the first assumption itself we had assumed gamma equals to beta equals to 1. Okay. So, therefore, we find that for the situation where gamma equals to beta equals to 1, for that particular case phi L square is nothing but dl by d whole to the power n minus 5, phi g square will be equal to dg by d whole to the power n minus 5. Okay. Where what is n? This n we have arrived at this n from the basic equation relating friction factor and Reynolds number by a Blochius type of relation. For laminar flow, what is the value of this n? And for turbulent flow, what is the value of this n if we assume Blochius equation? 0.25 or 1 by 4th. Fine. So, now for n equals to 1. So, therefore, for laminar flow n equals to 1. In that case, what is the relationship, or what is 1 by phi L square plus 1 by phi g square, can you tell me? Or sorry, 1 by phi L square whole to the power half, 1 by phi g square whole to the power half. What is this equal to, can you tell me? This is dl by d 5 minus dl by d, I have made it, yeah, 5 minus 1 whole to the power half. It should be 1 minus 5, I believe. It's all right, it's all right, 5 minus 1, fine, plus dg by d 5 minus 1 whole to the power half. So, therefore, this becomes 4 by 2 square, is not it? So, therefore, dl by d whole square plus dg by d whole square. Now, tell me one thing, suppose it is this type of a thing and this is dg hydraulic diameter and this is dl, then dg by dl, or rather dg by d whole square, this is equal to ag by a whole square, yes or no? Yes, and this is equal to ag by a whole square, sorry, very sorry, ag by a equal to alpha void fraction. So, therefore, this can be written down as 1 minus alpha, this can be written down as alpha, yes or no? So, therefore, this is equal to 1. Agreed? So, for laminar flow, what have we arrived at? We have found that for laminar flow 1 by phi L square whole to the power half plus 1 by phi g square, these are all capital, this is equal to 1. And for turbulent flow, we have to find out n equals to 1/4. isn't it? So, there we have to find out that what will be this particular coefficient such that 1 by phi L square whole to the power something plus 1 by phi g square whole to the power something, that comes to be equal to 1. Okay. Now, if you try out and if you see, you will find out that this particular coefficient, if it is made 19 by 8 by 19, okay, then probably you are going to get 1 by phi L square whole to the power 8 by 19 plus 1 by phi g square whole to the power 8 by 19 equals to 1. You can try it for yourself and you can see it. When n equals to 1/4, then in that case your phi L square, here you are supposed to put 1/4, isn't it? So, if you put 1/4 here, then what do you get? It is 19 by 4. Here also you get 19 by 4, isn't, sorry, minus 19 by 4 rather. Okay. So, therefore, if you have to write it in this particular form, then in that case it has to be multiplied by 8 by 19, fine. Then in that case you get a form of dl by d whole square plus dg by d whole square, this form, and finally it becomes equal to 1. Okay. So, for turbulent flow, assuming n equals to 1/4, we find that 1 by phi L square whole to the power 8 by 19 plus 1 by phi g square whole to the power 8 by 19. This is nothing but equal to dl by d minus 19 by 4, let me put it other bracket, into 8 by 19 plus dg by d again minus 19 by 4, 8 by 19. So, this reduces to dl by d whole square plus dg by d whole square, which is nothing but 1 minus alpha plus alpha equals to 1. So, therefore, for turbulent flow, assuming n equals to 1/4, under this condition we find the relationship is going to be 1 by phi L square whole to the power 8 by 19 plus 1 by phi g square whole to the power 8 by 19. This is equal to 1. Which one? dl by d, this is going to be, just let me check this up, dl by d 5, yeah, sorry, very sorry, very sorry, both of them are going to be plus. Agreed? Small mistakes are with so many calculations it comes up, but if you make the mistakes in the midsem, then I am not going to pardon you. That is the sad part of this story. Okay. So, anyhow, so therefore, we find that in this particular way, starting from the basic derivation, okay, basic derivation means the basic definition of phi L square, phi g square, the basic definition of the pressure gradient expression for the liquid occupied portion of the pipe, and when that liquid occupies the entire cross section of the pipe, for gas occupied portion of the pipe, and when that gas flows alone in the pipe, just from the basic derivations, basic definitions if we start, we arrive at some sort of an analytical expression between phi L square and phi g square. The initial attempt, as I have already told you, the initial attempt was this particular graphical correlation which I have showed in this particular graph, and this probably explains why I have express this graph in the form of 1 by phi g square and 1 by phi L. This should have been phi L square. This has been expressed in this form because from the analytical expressions also we find that the relationship between these two exists. The straightforward relationship exists not between phi g square and phi L square, but between 1 by phi g square and 1 by phi L square. Okay. So, this was the particular expression that we had got, and the analytical form can be expressed as it is written down here. It is 1 by phi L square whole to the power 1 by m. Remember, this m is different from the n, which was the which was the coefficient of Reynolds number in the friction factor Reynolds number equation when the equation is in the form of a Blochius type expression. please remember the main problem is when we have increased the number of phases, the number of properties, the number of constants, the number of exponents have increased. If you do not confuse them, then two phase flow is not going to be a very difficult subject for you. Okay. So, therefore, remember the analytical expression that has been expressed as 1 by phi L square whole to the power 1 by m plus 1 by phi g square whole to the power 1 by m equal to 1, where as we have already derived m equals to 2 for laminar flow, is not it? We have already derived that if it is on the basis of a Blossius type expression, then it comes to m will be equal to 19 by 8, which is nothing but 2.375, and this is your home assignment. You try to calculate the turbulent flow case on a mixing length basis and find out what is going to be the value of m in that particular case. You will find that the value of m under that particular condition is going to be 2.5, and more or less with experimental data they have found it varies from 2.5 to 3.5. Okay. So, therefore, this is the analytical expression of the graphical correlation which was originally proposed, but now of course, this analytical expression that is much more used. Fine. Now, before I proceed, I would just like to, the thing which I had told you, see when you are using a correlation you must also know how accurate it is, that is also very important. Okay. So, now let us see, we will take up the case of the annular flow pattern. This is the most, or rather the most common example for a separated flow situation, is not it? So, horizontal annular flow pattern, we make a few assumptions. What are the assumptions that we made for the derivation? We would like to find out phi L square for the annular flow pattern in a horizontal pipe. Okay. So, we will find out the phi L square from the separated flow model, and we will consider the actual annular flow situation and try to find out the phi L square there. Then we will compare the two values, and then we will see how accurate the separated flow model is. Now, whenever we take up any particular analysis of any particular flow situation, we try to take up the idealized form. Even in single phase flow you have found out what we try to do, frictionless flow, inviscid flow, okay, because the derivations are easier here. When we take up the annular flow pattern, what we assume? We assume that the liquid flows only as a film at the wall. There is no entrainment of the liquid by the gas core. Again an extremely idealized situation, remember it. There you will hardly find annular flow in with a case where there is no entrainment of liquid droplets in the gas core. Okay. Under most circumstances there is a good amount of entrainment, and sometimes the entrainment is so very high that we can hardly differentiate between bubbly flow and annular flow. It happens at times. Okay. But for the time being, for our assumption, we rather for our derivation, we assume two things. One is the liquid flows entirely as a film, which is an annular film between the gas core and the pipe wall. The second thing which we assume is the interface is smooth. Again it is quite a drastic assumption. Such an annular flow occurs only for very high gas and very low liquid flow rates. For most of the cases this does not happen, okay? But we assume these two conditions. So, the things which we assume is interface is smooth, entire liquid flowing as a film, flowing as an annular film between the gas core and the wall. It is going to be a horizontal pipe, so that there is no gravitational pressure gradient. It is going to be an air liquid or an air water system, so that there is no phase change, and there is the acceleration pressure gradients can be minimized. It is a circular pipe of conduit diameter d, so that the acceleration pressure gradient due to area changes are negligible. So, with all these assumptions we find out that we are in a position to apply the separate cylinder model to this particular type of annular flow situation. So, for such an annular flow situation, so if we can represent it, it is sort of this. very straight lines I have drawn. This is a gas core, this is a liquid film. Okay. If flow occurs in this particular direction, then wall shear stress will be in this particular direction, and there will be a tau I in the interfacial shear. What will be the direction of tau I? Can you tell me? Can you tell me the direction of tau I? Very correct. It will be in the direction of flow for the gas phase. No, good. It will be in the direction of flow for the liquid phase and opposite to the direction of flow in the gas phase, because the gas always flows faster than the liquid phase. Very correct. So, therefore, this is going to be fine. This is tau I, this is tau I, and suppose just like I do in the single phase flow case, here it is P, here it is going to be P plus dP, and this is a dz portion that is there. The entire pipe diameter is d. Agreed? Okay. So, in this particular case, the assumptions which we have is, and I have already discussed them, entire liquid flowing as symmetrical, and see, this is also a drastic assumption as far as horizontal flow is concerned, because whenever we consider horizontal flow due to gravity, most of this time it happens that the upper film will be thinner than the bottom film. Okay. But when the gas flow rate is quite high, liquid flow rate quite low, under that circumstance the distribution tends towards symmetric. So, since we have considering the other assumption, the symmetrical is quite a justified flow. Okay. The first thing, entire liquid flowing as symmetrical annular film, okay, between the channel wall and the gas core. The second assumption is smooth interface. Smooth interface between film and gas core. Third, it is not an assumption, it is a consideration, it is a horizontal pipe. So, therefore, gravitational pressure gradient minus dP dz g small g, this is equal to 0, okay, and this is, so therefore, this is steady isothermal axisymmetric horizontal flow. In short, we can write it in this particular way. Okay. Now, suppose we do the force balance on the combined two phase system. Okay. So, from force balance, just like if you remember we used to do for the single phase flow, we take a control volume, the pressure gradient and the wall shear stress, and then we used to balance them and we used to get an expression for tau w in terms of dP. Same way, okay, force balance on combined phase. What will we get here? We will get minus dP dz frictional two phase. This is simply 4 tau w two phase or tau w here divided by d. Yes or no? Agree? You can put it two phase if you want. We have always been doing it. Now, force balance on gas phase, force balance on a combined phase. Now, if we just take the gas phase alone, then what will we get? We will get minus dP dz f, the gas portion, this is equal to minus dP dz f two phase, which is will be equal to, can you see what I am writing? This is 4 tau I, okay, I will write it in the, I will write it here, equals to 4 tau I divided by d minus 2 delta whole square. Do you understand what I have written? Sorry, there is no whole square here. Is this portion correct? the portion which I have written down here. This portion is fine. Okay. Now, again what do I know? Just see, the thing is, if you have to understand these things very clearly, you have to keep the assumptions of separated cylinder model very clearly. You have to remember when you are using or when you are finding out the friction for liquid occupied or the gas occupied portion, when both the phases are flowing together in the pipe, and when you are considering when only that liquid is flowing alone in the pipe and only the gas is flowing alone in the pipe. If you do not confuse between these things, then the derivations are very simple, but moment you confuse these things, you are gone. Okay, so you have to remember certain situations. What are the situations that you are considering? One is a two-phase flow situation. Even if it is a two-phase flow situation, the liquid phase is flowing separately, the gas phase is flowing separately. If it is a separate cylinder model, then the liquid phase and the gas phase, they do not interact with one another. Fine. So, therefore, under that circumstance, the frictional pressure gradient in the liquid occupied portion will be equal to the frictional pressure gradient in the gas occupied portion, and this will be equal to the frictional pressure gradient in the two-phase separated flow situation. Please remember these things, I am repeating it repeatedly, so that you do not have any confusions regarding. The other thing which I am considering is, this particular liquid is flowing alone in the pipe. This particular gas is flowing alone in the pipe. So, when it is flowing alone, how do we denote it? It is just a capital L or a capital G as a subscript, and when it is flowing together in the two phase mixture, it is liquid portion or the gas portion in the subscript. If you want, you can use some other subscripts, I do not have a problem, but use some consistent nomenclature, so that you do not get confused at the end. Agreed? So, therefore, from here what do we get? From this particular horizontal flow, if you see, so we find out that from force balance on the combined phase and from force balance on the gas phase, we have obtained two expressions. Okay. Again we know minus dP dz frictional when this particular liquid is flowing alone in the pipe. Once we have liquid flowing alone in the pipe and the liquid flowing as the film, moment we get the two expressions of pressure gradient, we can divide one by the other and obtain phi L square. Okay. So, therefore, this dP dz frictional for liquid flowing alone in the pipe, this would be equal to 4 tau W L by D. Same way, first we obtain two phase flowing, then the gas phase for that particular situation, and now we have found it out minus dP dz FL. So, if this FTP is divided by this particular FL, then we can get phi L square. Agreed? So, therefore, if we divide one by the other, what do we get? We get phi L square. This is minus dP dz frictional two phase by minus dP dz FL. So, this is nothing but equal to tau W Tp by tau W L. Yes or no? Agreed? And now, what is this equal to? This is FTP rho L U liquid portion square by 2 divided by FL rho L U L square by 2. Yes or no? Okay. Where this tau W Tp, it is the wall shear stress when the two phases are flowing as separated flow in the pipe, and this is the wall shear stress when the liquid is flowing alone in the pipe. Agreed? Fine. So, now you tell me a few things. This U liquid portion by when this U is flowing alone in the pipe, that means this UL, it is nothing but QL by A. Yes or no? Fine. Or in other words, this can be taken as JL, volumetric flux, isn't it? So, this can be written down as U liquid portion by J liquid portion. Can I write down this or not? Tell me. Okay. And what is the relationship between these two? Isn't it equal to 1 by 1 minus alpha? You remember this? Fine. So, therefore, from here phi L square, if I substitute it here, what do I get? Phi L square, this is equal to F T P by F L into U liquid portion by J liquid portion whole square, or in other words this is equal to F T P by F L 1 by 1 minus alpha whole square. Yes or no? Okay. So, we have a small portion of this left which we can continue in the next class, a very small portion of this left. So, we will be doing this in the next class. We will be deriving the phi L square for this actual annular flow situation, and we will find out the phi L square which we can obtain from the separated flow model, and we will compare the two. This we will be doing in the next class, and then we will be proceeding further for certain other things. So, thank you very much.